What if I told you that absolute darkness doesn't exist? That the totally ordinary click of a light switch before bed isn't the end of the world in your room, but just the beginning of a hidden, invisible quantum storm? We're used to thinking that light can just be turned off, like shutting off a faucet. Boom, and it's gone. But what if that's just a convenient illusion that our brains blindly believe because of our own biological limits? Where do the trillions of particles vanish to without a trace? Particles that just a fraction of a second ago were ripping through space at nearly 300,000 kilometers per second. Can colossal energy just evaporate, leaving no trace, no sonic boom, no echo? Or has the light not gone anywhere this whole time, but instead permanently stamped itself into the walls of your bedroom, forever changing the very structure of the matter around you? Today, we're going to ditch our everyday habits and look at this process through the lens of the harsh laws of physics, laws that are the same for everyone and have no patience for magic or vanishing acts. We'll track the last photon from the glowing filament of the bulb to its fatal collision with reality. And the main question we'll try to answer is, when the light goes out, does it actually die? Or do we just lose the ability to see its new form? Let's meticulously break down that exact second when the electrical current stops flowing to the lamp. The superficial, everyday understanding of this process says that the light disappears absolutely instantly. We press the plastic switch, and the room is immediately plunged into darkness. Our vision and our brains work in perfect tandem to create this seamless illusion of complete and immediate disappearance. It takes the human eye about 13 milliseconds to process a visual image and send it to the visual cortex of the brain. For our nervous system, that's the speed limit, our own frame rate. Anything that happens faster than those 13 milliseconds blurs into one indivisible instant for us. But the problem is that for the universe itself, this human instantly simply doesn't exist. What feels like one brief flash to us stretches out into an incredibly complex and action-packed sequence of physical events on a fundamental level of reality. To truly understand where the light goes, we first need to radically scale down our perception. We need to slow time down as much as possible. Imagine we have a hypothetical, ultra-precise stopwatch capable of ticking off not seconds, not even milliseconds, but nanoseconds, billionths of a single second. On that fantastical timescale, the click of a switch wouldn't sound like a sharp, abrupt snap, but like the slow, dragging grind of tectonic plates. The metal contacts inside the plastic housing of the switch begin their slow journey away from each other. The flow of electrons, which until now had been running non-stop and packed tightly through the copper wires, powering the whole system, starts to dry up and then gets cut off entirely. This power cut, traveling down the wires, eventually reaches the tungsten filament inside the glass bulb of the lamp. Let's take a closer look at this filament. Just 1 nanosecond ago, it was a literal hellscape. Because of tungsten's massive electrical resistance, the current flowing through it heated the metal to unbelievable temperatures, over 2,500 degrees Celsius. The tungsten atoms in the crystal lattice were vibrating frantically, crashing into each other, and this colossal kinetic energy forced them to continuously dump their excess excitement. They did this by blasting myriads of photons into the surrounding space, those exact elementary particles that make up the light we see. But now, the current has run dry. The filament is no longer getting an energy feed from the outside. The electrons have stopped pushing the metal atoms. However, the filament is still unbelievably hot. Thermal inertia won't let it cool down to room temperature in a fraction of a second. The tungsten atoms keep vibrating on momentum, gradually, step by step, slowing their dance. And as they slow down, they are still forced to emit light, shedding the last of their stored energy. At first, this light is blindingly white. Then, as the temperature drops, it shifts into the yellow spectrum, then into red, and finally transitions into invisible infrared radiation. To our naked eye, this whole fading process happens imperceptibly fast. But in the world of nanoseconds, the lamp dies slowly and reluctantly. It fires off its last, final volley of photons. This volley breaks away from the hot glass of the bulb and rushes into the space of your bedroom with unimaginable speed. And this is where the strangest and most paradoxical part begins. The switch has already clicked. The power source is dead. But the room, in this exact nanosecond, is still full of light. Trillions upon trillions of light particles are in the air right now. They are flying from the lamp to the wallpaper, to the wooden closet, to the ceiling, and to your face. The light has physically detached from its creator and now exists completely autonomously. But why don't we see this light hanging in the air, slowly settling to the floor, or smoothly dissipating like gray smoke from a blown-out candle? The answer lies in the unimaginable, monstrous speed at which the subsequent events unfold in this enclosed space. As we know from basic physics, the speed of light in a vacuum is the absolute speed limit for our universe, clocking in at roughly 300,000 kilometers per second. In the air filling your room, it's only a tiny fraction of a percent slower. But for the scale of a living space, that difference is totally insignificant and plays no role whatsoever. 300,000 kilometers per second. It's easy enough to say those words out loud, but our brains, which evolved over hundreds of thousands of years to track running antelopes, flying wooden spears, and falling rocks, are physically incapable of comprehending and digesting this colossal number. To try and picture it, we need massive analogies. In one single second, a beam of light can travel around the Earth's equator exactly 7.5 times. In 1 second, it can make the trip from the Earth to the Moon. Now let's mentally take this cosmic, universal speed and cram it into the scale of a normal bedroom. Let's say the distance from one wall to the opposite one is exactly 5 meters. In the time it takes you to blink one eye, a flying photon manages to travel tens of thousands of kilometers. In the enclosed space of your bedroom, this tiny bundle of pure energy crosses the distance from the light bulb to the wall in an absolutely unfathomable fraction of time, in about 15 billionths of a second. However, a photon doesn't necessarily die upon its first collision with an obstacle. Light has the amazing ability to bounce off surfaces, and your room, from a quantum mechanics perspective, turns into the craziest, most chaotic, high-speed billiard table in the entire universe in that instant. Photons smack into the wallpaper, bounce off the glass mirror on the closet door, ricochet off the white ceiling, and hit the varnished hardwood floor. If we had supervision and could watch this process from the outside without being part of it, a normal room would look like a buzzing energy hive, filled to the brim with laser beams intersecting at every possible angle. A photon darts from one obstacle to another with such fury that, given the average size of a room and the constant speed of light, a single particle can bounce off the walls over 60 million times in just 1 second. 60 million wall strikes every single second. But if light can bounce around the room for so long and so stubbornly, why does darkness hit us instantly? Why doesn't the room glow with an afterglow for at least a couple of minutes? This is where the harsh math of absorption comes into play. The walls of your room are far from perfect mirrors. Every time a photon hits the surface of paper wallpaper, cotton fabric, or rough wood, a highly complex physical interaction happens at the atomic level. A portion of the photons really does bounce back into the air, changing their angle of reflection according to the laws of optics. But a massive, overwhelming majority of the light particles are absorbed by the material permanently, right at the moment of impact. Let's imagine an idealized situation. Let's say your light-colored wallpaper reflects exactly 50% of the light hitting it. That means that upon the very first collision of the light wave with the wall, half of all the flying photons vanish from the room's space. The remaining half ricochets and flies toward the opposite wall at the same unbelievable speed. On the second strike, another half of those remaining vanishes. Then, on the third strike, half of that quarter vanishes. The decrease in the amount of light happens like an avalanche, obeying a strict and ruthless mathematical exponential curve. Let's do the math. After just 10 bounces off the walls, less than 0.1% of the original light emitted by the lamp will be left in the room. And after 20 consecutive bounces, the original light will be almost completely gone, dissolved into the materials of the walls and furniture. Now let's recall our previous number. A flying photon makes 60 million bounces in 1 second. That means those fatal 20 bounces needed to completely destroy the light will take such a vanishingly small fraction of time that no biological eye, no perfectly wired neural circuit in any living creature's brain could ever register this transition period. Light doesn't disappear by magic, and it doesn't dissolve into the void. It just rapidly hammers itself into the walls, absorbed by them over the course of millions of lightning-fast ricochets that manage to happen in a single, tiny millionth of a second after you flip the plastic switch. This reminds me of the story of how global science even came to understand this elusive speed in the first place. After all, for many centuries, the greatest minds of humanity, from ancient philosophers to René Descartes, genuinely believed that light traveled absolutely instantaneously. It was thought that a beam of light was something like a solid stick. If you push one end, the other end moves in that exact same second. Proving the opposite and measuring the speed of something that seems omnipresent was an incredibly ambitious and difficult task. One of the most beautiful, elegant, and monumental experiments in the history of physics was conducted by the American scientist Albert Michelson. In 1926, he decided to measure the speed of light with unprecedented, unbelievable accuracy for the time. Michelson quickly realized he couldn't use a closed laboratory for this. Light was too fast for any cramped walls. It would fly past them faster than any mechanical device could click. The scientist needed the scale of an entire mountain landscape. He placed a powerful, bright light source on the peak of Mount Wilson in California, and on the peak of another mountain, Mount San Antonio, located at a strictly measured distance of exactly 35.4 kilometers from the first, he set up a stationary reflecting mirror. But the main, truly genius element of his engineering design was a special 8-sided rotating mirror set up on the first mountain next to the light source. The core of this experiment was stunning in its mathematical simplicity and technical complexity. The beam of light hit one of the faces of the rotating mirror, reflected off it, and flew 35 kilometers to the second mountain, There, it hit the stationary mirror, turned around, and flew back. Ideally, it was supposed to hit the next face of that exact same rotating mirror and reflect into the eyepiece of the observer's telescope. But since the first mirror was continuously spinning at a massive speed, during the short time the light was flying there and back, which was over 70 kilometers of travel through the atmosphere, the mirror had time to rotate a bit on its axis. If the rotation speed was wrong, the light would just fly off to the side. Michelson, using custom-built powerful pneumatic engines running on compressed air, spun his 8-sided mirror up to a mind-boggling speed of 528 revolutions per second. It howled as it sliced through the air. The scientists meticulously fine-tuned the rotation speed until the light beam returning from afar hit the exact center of the telescope's eyepiece. This meant that during the light's flight time, the mirror had rotated by exactly 1/8 of a turn. Knowing the absolutely precise distance between the two mountain peaks and the absolutely precise rotation speed of the mirror prism, Michelson was able to use simple math to figure out the time the light spent on this long journey. His final result, 299,796 kilometers per second, became a colossal triumph for early 20th century experimental physics. This epic experiment, which took years of effort, building special geodesic towers in the mountains, perfectly calibrating the optics, and accounting for atmospheric distortion, finally and definitively proved one fundamental truth. Light is a traveler in space. And like any moving traveler, it has a strict, finite speed, which means it inevitably needs time to get from its departure point to its destination. Understanding this fundamental fact completely flips our perception of everyday things. When you turn off the lamp on your desk, you don't wipe out the existence of light in the room in one fell swoop. You are just closing the faucet that the stream of photons is pouring out of, and the particles that already managed to fly past the glass are still on their way. They continue their frantic journey, piercing the air, bouncing off your pillow, refracting through the window glass. Darkness doesn't fall because we simply cut off light's path to existence. Darkness falls because the remnants of that light were rapidly, ruthlessly, and completely absorbed by something. And here we are, faced with the next, much deeper and more paradoxical mystery. We figured out the timing. We understood the mechanics of speed. We established that light needs a few millionths of a second to completely smash into every possible obstacle. But what exactly happens the moment of the impact itself? Where does this frantic kinetic energy of the flying particle go when it finds its final resting place on the matte surface of your wall? Can something material, ripping along at almost 300,000 kilometers per second, just up and vanish, dissolve, without leaving a physical dent or a visible trace? To answer this question, we'll have to step away from the familiar macroscopic scales of meters, seconds, and flying particles. We have to figure out what exactly a light beam is before we try to comprehend its death. And in the next chapter, we will dive into the history of how science first realized that light is not just a stream of invisible projectiles, but a profound vibration of space itself. So, we left our beam of light at its most dramatic moment. Millions of elusive particles, having broken away from the cooling tungsten filament, are ripping through the space of your bedroom at unimaginable speeds and slamming head-on into an impassable barrier, the surface of your walls. But before we try to process the death of light, it is absolutely critical that we understand what exactly it is while it's alive. What exactly is flying through space? And what exactly is crashing into the wallpaper? To answer this, we need to take a step back and look at the history of human thought. For centuries, the greatest minds on our planet waged fierce debates over the fundamental nature of light. Isaac Newton, whose authority in the scientific world was absolute, argued that light consists of tiny, elusive particles. He called them corpuscles. According to Newton, a glowing object is like a machine gun constantly firing microscopic solid projectiles. These projectiles fly in a straight line and bounce off mirrors following the exact same rules of geometry that a billiard ball uses when bouncing off the bumper of a table. On the other hand, his contemporary Christian Huygens categorically disagreed with this view of the world. He pointed out that if you cross two beams of light, they don't crash into each other the way streams of flying rocks would. They pass right through each other completely unhindered. Huygens proposed that light isn't a stream of particles, but a wave, a kind of tremor propagating through an invisible medium. For a long time, these two concepts were locked in irreconcilable conflict. But the real breakthrough that permanently changed our understanding of reality happened in the mid-19th century. In 1865, the Scottish physicist and mathematician James Clerk Maxwell published a paper that became one of the greatest intellectual achievements in human history. The most mind-blowing part is that Maxwell initially had no intention of solving the mystery of light at all. He was interested in completely different phenomena: electricity and magnetism. At the time, electricity and magnets seemed like strange, but separate forces of nature. Scientists already knew that if you ran an electrical current through a wire, a compass lying nearby would twitch its needle. So electricity somehow generated magnetism. Michael Faraday, a brilliant English experimentalist, went even further. He proved the reverse. If you move a magnet inside a coil of wire, an electrical current is generated in the wire. A changing magnetic field spawned an electric field. James Clerk Maxwell took these scattered observations and translated them into the strict language of higher mathematics. He created the system of famous equations that bear his name today. And when he finished his calculations, a picture of stunning beauty unfolded before him. The equation showed that electricity and magnetism aren't two different forces, but two sides of the same coin, a unified electromagnetic entity. But the main discovery was yet to come. Maxwell realized that if you create a changing electric field, it instantly spawns a changing magnetic field. And that changing magnetic field, in turn, instantly creates a new changing electric field. An endless chain reaction is born. These two fields begin to latch onto each other, pulling themselves out of the void, weaving together in an endless dance. They form a wave that can detach from its source and travel through space on its own. Maxwell, being a brilliant mathematician, calculated the speed at which this electromagnetic wave should rip through the void. And the result of these calculations made the scientific world tremble. The speed of this theoretical wave was exactly 300,000 kilometers per second. The number perfectly matched the speed of light that astronomers had measured earlier. It couldn't be a simple coincidence. Maxwell drew a monumental conclusion. Light is an electromagnetic wave. It's not flying solid beads, as Newton thought. Light is a rhythmic, pulsating tremor of space itself, made up of interwoven electric and magnetic fields. Let's break this concept down a bit more and try to visualize it using a simple real-life analogy. Imagine a huge, calm lake. The surface of the water is absolutely smooth. This water represents the invisible electromagnetic field that permeates our entire universe. On its own, the field is invisible and doesn't manifest itself in any way, as long as it's at rest. Now imagine you take a rock and throw it right into the center of the lake. The rock hits the surface of the water with a splash. This impact is the analog to what happens in the tungsten filament of your light bulb when the electrical current forces the metal atoms to vibrate frantically. The vibrating charge disturbs the peace of the invisible electromagnetic field. What happens on the lake next? Concentric circles, waves, start radiating outward in all directions from where the rock fell. The water itself isn't flowing anywhere. Its currents aren't rushing toward the shores. Every single drop of water is just bobbing up and down. But it's exactly this rhythmic oscillation that gets passed from one drop to the next, forcing the wave to relentlessly move forward. Light behaves the exact same way. When you turn on a lamp, you create a disturbance in the electromagnetic field, and waves of invisible tension start radiating outward from the lamp in all directions. There's no physical matter in these waves, no mass. It's pure geometry and pure energy, transmitting through space. This realization leads us to another mind-blowing fact. What we are used to calling light is just a tiny, insignificant sliver of reality. Human vision is incredibly limited. Our eyes can only detect electromagnetic waves within a very narrow range of wavelengths. The distance between the crests of the waves we can see ranges from 400 to 700 nanometers. A nanometer is 1/1000th of a meter. If the wavelength is around 700 nanometers, our brain interprets this signal as the color red. If the wavelength is shorter, around 400 nanometers, we see the color violet. All the other colors of the rainbow, orange, yellow, green, light blue, and dark blue, neatly fit into this narrow gap. But the electromagnetic ocean is infinite. If the wavelength gets just a bit longer than that of red light, the wave becomes invisible to us. It turns into infrared radiation. We can't see it with our eyes, but we can feel it on our skin as the heat radiating from a hot stove. If you stretch the wave even further, to a few millimeters, or even meters, it becomes a radio wave. The exact same radio waves that are currently carrying a Wi-Fi signal to your smartphone, or broadcasting music to your car antenna. That is the exact same light, just with a very long distance between the crests. Conversely, if you compress the wave so the distance between crests is less than 400 nanometers, it turns into ultraviolet radiation, the kind we block out with sunglasses. Compress it even more, and you get X-rays, capable of seeing right through our bodies. Even more, and you get gamma radiation, packing colossal destructive power. All of this, radio, heat, X-rays, and visible light, is the exact same physical phenomenon. It is a ripple on the surface of the exact same invisible lake. But how did scientists prove Maxwell's calculations were right? How did they confirm the existence of this invisible electromagnetic spectrum? In 1887, the German physicist Heinrich Hertz ran an experiment that permanently cemented his name in the history of science. He decided to create invisible light in his lab. Hertz built a device consisting of an electrical circuit with a small gap between two metal spheres. When high voltage was applied to the circuit, a bright electrical spark jumped between the spheres. According to Maxwell's theory, this sudden electrical discharge was supposed to spawn a powerful electromagnetic wave, a tremor of space invisible to the eye. To catch this theoretical wave, Hertz set up a receiver at the other end of the room, a simple copper ring, also with a tiny gap. These two devices were not connected by any wires. They were several meters apart. When Hertz turned on his spark gap transmitter and a spark jumped between the spheres, a miracle happened. At the other end of the room, in the completely isolated copper ring, a tiny, barely visible spark also jumped. An invisible force crossed the space of the laboratory and forced the electrons in the metal ring to move. Hertz had successfully generated and caught radio waves. He proved that Maxwell's electromagnetic waves were absolutely real. By the way, Heinrich Hertz himself had absolutely no idea about the potential of his discovery. When students asked him what practical use these invisible waves might have, he replied that it was a completely useless phenomenon, serving only to confirm the mathematical correctness of James Clerk Maxwell. He had no clue that his sparks would become the foundation for the creation of radio, television, cellular communications, and our entire modern information society. But let's go back from Hertz's lab to our dark bedroom. If we adopt the classical view of the nature of light, we have to perceive the beam from the lamp not as a stream of solid projectiles, but as a continuous electromagnetic wave, as a tremor of an invisible field. In that case, what does the death of light mean at the moment it collides with a wall? From the perspective of wave physics, everything seems quite logical. Picture our pond and the radiating waves again. The waves ripple across the surface of the water and eventually hit the shore. The shore, in our analogy, is the surface of your wallpaper. When the electromagnetic wave hits the wall, its pulsating electric and magnetic fields penetrate into the material. The wall is made of atoms, and inside, every atom are charged particles, electrons. The electric field of the wave starts jerking these electrons side to side, forcing them to oscillate in time with its own pulsations. The wave gives up its energy to rock the matter of the wall. Just like an ocean wave loses its power crashing against coastal rocks and tumbling pebbles on a beach, the electromagnetic wave of light gradually fades away, transferring its energy to the atoms of the wallpaper. In this worldview, the process of turning off the lamp just means we threw the final rock into the pond. The lake stopped receiving new disturbances. The last, final crests of the waves ripple from the center to the edges of the room, hit the shore, force the electrons in the wall to make a few forced oscillations, and the process is over. The wave dies down. The lake of the electromagnetic field becomes absolutely smooth and still again. Complete, serene darkness falls. This worldview, created in the 19th century, was incredibly beautiful, logical, and mathematically flawless. It seemed physics had completely and definitively explained the nature of light. Many scientists of the time genuinely believed that fundamental science was coming to an end, and future generations would just be tweaking the values of constants out to the 6th decimal place. Light is a continuous wave. Darkness is the absence of a wave. Everything is simple and clear. But nature turned out to be far more complex and inventive than Victorian-era researchers could have guessed. The classical wave-based view of light harbored a hidden threat. Soon, physicists started running new, more nuanced experiments with heated bodies and ultraviolet radiation. And the results of these experiments absolutely refused to fit into Maxwell's beautiful and elegant equations. The continuous wave suddenly started behaving as if it wasn't a wave at all, but rather a stream of those exact same particles Isaac Newton had once talked about. A quantum revolution was coming. Understanding exactly how light dies will require us to abandon familiar logic and accept that the universe, at its deepest foundations, is discrete. Light doesn't flow in a continuous stream. It shatters into the tiniest indivisible packets of energy. And in the next chapter, we will figure out why the classical wave was forced to become a quantum particle, and how this discovery forever changed the fate of every flying photon in your room. We left off with physicists feeling incredibly confident in their knowledge by the end of the 19th century. James Clerk Maxwell's equations brilliantly proved that light was a continuous electromagnetic wave, It seemed the picture of the universe was practically complete. Leading professors of the era seriously advised young, ambitious students not to go into theoretical physics because supposedly all the major discoveries in the field had already been made. They thought all that was left was to tweak a few minor details and measure already known constants with a bit more precision. Light seemed like a perfectly understood phenomenon, a smooth, continuous ripple on the surface of an invisible cosmic ocean. But in science, it always goes like this. The second you decide you understand absolutely everything, nature throws you a curveball that burns the old world to the ground. This curveball came from a completely unexpected angle, from engineers trying to build more efficient electric light bulbs in industrial furnaces. The problem they ran into went down in the history of science under the terrifying name of the ultraviolet catastrophe. To understand the core of this catastrophe, we need to picture the concept of a so-called absolutely black body. In physics, an absolutely black body is an idealized object that completely absorbs all light hitting it and reflects nothing. But at the same time, if you heat this body up, it starts radiating energy itself. In practice, the closest thing to this mathematical abstraction is a regular enclosed oven with a tiny peephole in the wall. If we peek into that hole at room temperature, we see absolute darkness. But if we light a fire in the oven and crank up the heat, what happens is something every blacksmith or potter has seen. First, the inside of the oven starts radiating invisible infrared heat. Then, as it gets hotter, it begins to glow faintly with a dim, dark red color. If we push the temperature even higher, the color turns bright orange, then yellow, and at incredibly massive temperatures, blindingly white with a slight bluish tint. The link between color and temperature seemed obvious and clear. Color is just the length of the electromagnetic wave. The hotter the object, the shorter the waves it can emit. Two brilliant British scientists, John William Strutt, better known as Lord Rayleigh, and James Jeans, decided to describe this everyday process using the strict mathematical formulas of classical wave physics. They derived a law that was supposed to predict how much light and exactly what color a heated oven would emit at any given temperature. Their logic relied on a simple idea. Inside a heated oven, electromagnetic waves should arise just as naturally as sound waves do in an organ pipe. But when they finished their calculations, the result was truly monstrous. According to the Rayleigh-Jeans law, it turned out that classical physics allowed for an infinite number of short waves. The math relentlessly showed that any heated body, whether it's the tungsten filament in a bulb, a red-hot coal, or even your own warm body, should instantly dump all its energy into the shortest waves possible, into ultraviolet, X-ray, and gamma radiation. If the equations of classical physics were totally correct, a normal kitchen oven wouldn't just glow red when you turned it on. It would instantly explode, firing off a blinding flash of lethal radiation packing infinite energy that would incinerate everything around it. The classical physics of Maxwell and Newton predicted an impossible, absurd world that couldn't exist in reality. The math said the oven should kill you with an X-ray beam, but the real-life oven peacefully warmed your hands and glowed with a soft orange light. This insurmountable contradiction between theory and practice was named the ultraviolet catastrophe. The scientific world hit a dead end. Maxwell's equations worked perfectly for radio waves, but broke down completely inside a glowing hot oven. The only person able to resolve this crisis was the German theoretical physicist Max Planck at the very end of 1899. And he did it using what he himself later called an act of desperation. Planck spent months banging his head against the formulas, trying to make them match real-world measurements. Finally, exhausted by the futile attempts, he plugged a mathematical trick into his equations, a totally artificial, unjustified assumption. Planck asked, what if light doesn't pour out of the oven walls in a continuous, unbroken stream? What if energy is radiated in strictly measured tiny packets? He called these indivisible packets of energy quanta. To grasp how radical this idea was, let's use an everyday analogy. Imagine water flowing from a faucet. The water looks like a totally continuous liquid to us. You can pour a full glass, half a glass, a quarter, or even a tiny drop. Classical physics viewed light exactly like that, as continuous water whose volume could be divided infinitely. But Planck's idea turned this stream of water into a stream of dry sand. Sand only looks continuous from a distance. If we look closely, we see it is made up of indivisible grains. You can't pour half a grain of sand. You have to add either one whole grain or none at all. Planck declared that light energy has the same grainy structure. The atoms of the oven wall can't emit a random amount of energy. They can only spit out 1 quantum, 2 quanta, 3 quanta, but never 1.5 or 2.3 quanta. The funny thing is that Max Planck himself didn't believe in the real physical existence of these quanta. To him, it was just a handy mathematical loophole, a cog in an equation that miraculously deleted the infinities and saved physics from the ultraviolet catastrophe. He hoped that someday in the future, someone would find a normal, wave-based explanation for it. But in 1905, a young, then unknown clerk at the Swiss Patent Office named Albert Einstein stepped onto the stage. Einstein carefully read Planck's work and did what the author himself didn't dare to do. He declared, "Quanta are not a mathematical trick. They are reality. Light really does consist of physical particles carrying energy." Later, these particles would be named photons. Einstein used this idea to explain another mysterious phenomenon, the photoelectric effect. Physicists of the time were running a weird experiment. They took a metal plate and shined a beam of light on it. It turned out that under certain conditions, light could knock electrons out of the metal, creating an electrical current. But the classical wave theory failed once again. If you shined a very powerful bright red spotlight on the metal, nothing happened. The electron stayed put. Red light, having a long wavelength, should have, according to continuous wave logic, gradually built up its energy in the metal, the way an ocean wave rocks a heavy ship. Sooner or later, an electron should have built up enough force to fly out. But that didn't happen, even after hours of blasting it with red light. However, the second they pointed a very weak, dim beam of violet light at the exact same plate, the metal instantly started sparking with ejected electrons. The violet light knocked electrons out in the very same nanosecond, with no time needed to build momentum or hoard energy. Einstein explained this brilliantly and simply. If light is a stream of particles, then the photoelectric effect shouldn't be viewed as rocking on waves, but as shooting at targets. A photon is a bullet. Every photon of red light carries too little energy. It's a weak, slow bullet. No matter how many trillions of these bullets you fire from a red spotlight, not a single one of them individually has enough power to rip an electron away from its atom. The electron absorbs energy strictly from one hit. 2 red photons can't pool their efforts. On the other hand, violet light is made of high-energy photons. These are powerful, armor-piercing rounds. Even if the violet beam is dim, meaning there aren't many photons in it, Every single round that hits the target packs enough punch to instantly and violently knock an electron out of the metal. For this elegant and revolutionary explanation, Albert Einstein eventually won the Nobel Prize, and the American physicist Robert Millikan ran a series of ultra-precise experiments a few years later that unconditionally confirmed all of Einstein's calculations. And just like that, light, which in the 19th century looked like a perfect continuous wave, suddenly gained flesh. It became a particle again. And this led science to the concept of wave-particle duality, one of the hardest ideas to wrap your head around in all of quantum mechanics. Light behaves as both a wave and a particle at the same time. How is that possible? Imagine a regular metal cylinder. If you shine a flashlight on it from the side, a rectangular shadow will appear on the wall. An observer looking only at that shadow will state with absolute certainty, the object is shaped like a rectangle. But if you shine the light on the cylinder from above, a circular shadow will appear on the floor. Another observer will swear they are looking at a perfectly flat circle. Who is right? Both are right, and both are wrong. The true object is 3D, and the circle and rectangle are just its shadows in our 2D perception. It's the exact same thing with a photon. When a beam of light rips through the space of your room, it acts like James Clerk Maxwell's wave. It can bend around obstacles and refract through window glass. But the second it slams into the wall, it hits it not as a tremor smeared across space, but as Albert Einstein's solid, indivisible projectile, as a quantum of energy. We turn off the lamp, and the stream of these tiny energy bullets cuts off. The particles that already managed to fly out crash into the atoms of your wallpaper at massive speeds. And before we figure out what exactly happens the moment they collide, we have to ask ourselves a philosophical, almost terrifying question. What kind of particle is this anyway? How does a photon live from the moment it is born to the moment it dies on your wall? How does it experience time and space? Spoiler alert, the reality a photon exists in is so different from our everyday lives that it defies common sense itself. We'll talk about this weird, timeless life in the next chapter. Now that we've realized that light behaves like a particle the moment it hits your bedroom wallpaper, we need to try and understand the very nature of this particle. We are used to thinking in the categories of the tangible macro world. When we hear the word particle, our brain helpfully draws a picture of something small and solid, a grain of sand, a speck of dust floating in a sunbeam, or a tiny metal ball bearing. We intuitively assign any particle the properties of the matter we're used to. It has volume, it takes up a specific place in space, and most importantly, it has mass. But if you try applying this everyday common sense to a photon, you will fail completely. A photon isn't a speck of dust. It is an entity of a totally different order. The main defining characteristic of a photon, which makes it the most unique object in our known universe, is this. A photon has no rest mass. A photon's rest mass is absolute mathematical zero. Let's pause here and break this down a bit more, because it's not just a physics term. It's the key to understanding all of reality. What is rest mass? In everyday life, when you step on a scale, it shows your mass. You are standing still, you are at rest relative to the floor. Your body, made up of trillions of cells, which in turn are made of atoms, electrons, and quarks, has an internal resistance to changes in speed. That resistance is mass. If you put a normal rock on a table, it will sit there infinitely long, retaining its mass. A rock can exist in a state of rest. A photon, however, doesn't have this luxury. It has no rest mass for one simple reason. A photon is physically incapable of resting. It is impossible to stop it, place it on a quantum scale, and weigh it. A photon exists exclusively and entirely in motion. It is woven from pure motion, from pure kinetic energy. The exact second a photon stops by crashing into an obstacle, it ceases to exist. A light particle cannot slow down before impact. It cannot fly at 200,000 kilometers per second, then break down to 100,000 and gently settle onto the wall. Under any circumstances in a vacuum, it always moves at the maximum possible speed in the universe, the speed of light. To understand how this fact affects the life of our light particle, we'll have to turn back to the genius of Albert Einstein and his special theory of relativity, published in that same unbelievable year, 1905. Einstein derived the most famous equation in the history of science, which is known to absolutely everyone on the planet, even if they know nothing about physics. This equation states, energy equals mass times the speed of light squared. If we translate these dry mathematical symbols into normal human language, the equation says something staggering. Energy and mass are not different things. They are two forms of existence of the exact same phenomenon, like water and ice. Mass can be turned into colossal energy. All nuclear reactors and stars in space operate on this principle. Conversely, colossal energy can be compressed into mass. Since a photon's rest mass is zero, its entire existence, its entire physical flesh, is defined solely by its energy and speed. A photon is literally a bundle of concentrated energy flying through space. But the special theory of relativity brought another conclusion with it, one that blows your mind even harder. It permanently destroyed our concept of time as something absolute, steady, and the same for everyone. Einstein proved that time is relative. It is plastic. It can stretch and compress depending on how fast you are moving through space. Let's do a thought experiment. Imagine a person standing on a train station platform and a second person rushing past them in a high-speed train of the future. If the train were moving at a speed close to the speed of light, the observer on the platform would see something fantastical. They would notice that the clock in the driver's cabin was ticking monstrously slowly. The second hand moves as if it's fighting through thick syrup. What's more, from the perspective of the person on the platform, all processes inside the train would slow down. The passengers would move like they were in slow motion. Their hearts would beat slower. They would age slower. This is not an optical illusion or a broken clock mechanism. This is a fundamental property of the fabric of the universe called relativistic time dilation. The faster an object moves through space, the slower time flows for it relative to a stationary observer. This effect is absolutely real. It is constantly measured by physicists and particle accelerators and is factored in by engineers when tuning GPS satellites. Without adjustments for time dilation, the navigators on our phones would start making kilometer-wide errors in just a couple of days. But what happens if we push this thought experiment to its absolute limit? What if our train doesn't just get close to the speed of light, but actually hits it? Einstein's mathematical formulas give a clear but completely insane answer from the perspective of human experience. A zero appears in the denominator of the equation describing the flow of time. When the speed of light is reached, time stops flowing altogether. It halts completely. This is exactly what happens to our photon. Because it always moves at the speed of light, time simply doesn't exist for it. It never begins and never ends. Let's apply this fact to that exact light particle that broke away from the tungsten filament of your bedside lamp. From your point of view, as a stationary observer sitting on the bed, the photon flew a few meters and spent 15 billionths of a second on the trip. With ultra-precise equipment, you could clock the moment of its birth on the hot metal, track its straight-line path through the air in the room, and record the moment of its death as it hit the wallpaper. This event has a beginning, a duration, and an end. But from the photon's perspective, none of this happened. For a particle of light, the moment of its birth from the tungsten atom and the moment of its death in the paint on your wallpaper are the exact same instant. Not a single microsecond passed for the photon between these two events. It didn't experience the process of flying. It didn't feel the duration of its existence. This philosophical conclusion gets even more mind-blowing if we expand the scale of our thought experiment beyond a cramped bedroom. Imagine a photon that was born in the core of a distant star located in the Andromeda Galaxy. This photon broke free, left its home galaxy, and embarked on an incredible journey across the freezing, empty intergalactic abyss. It flew through the black cosmos for long epochs. Back on Earth, during this time, dinosaurs went extinct, mountain ranges rose and crumbled to dust. Humans evolved, built telescopes, and pointed one of them at the night sky. And then, 2.5 million years later by Earth time, this ancient cosmic photon hits the lens of an Earth telescope and is absorbed by the retina of an astronomer's eye. For the astronomer, this light traveled a distance of 2.5 million light years. It is an incredible, almost eternal story of flight. But for the photon itself, for the photon from the Andromeda Galaxy, the moment it shot out of the star's superheated plasma and the moment it died in a human eye on Earth happened absolutely simultaneously, without the slightest gap. Its entire life, which lasted millions of years for us, fit into one frozen 0 point for it. A photon is an entity locked outside of time. It is exactly this massless, timeless bundle of pure energy that is currently flying toward your bedroom wall in those brief moments after the switch clicks. But before we finally let it crash into an obstacle and end its story, we need to figure out one more crucial detail. Where did this photon even come from in the first place? After all, before you turned on the light, it didn't exist in nature. It wasn't lying inside the metal wire waiting for its moment. How does this bundle of energy get born out of lifeless dark matter? To understand the mechanics of how light is born, we'll have to peek inside the atom itself, to where the strict and uncompromising laws of the quantum staircase rule. We'll talk about this incredible process of creating something out of nothing in the next chapter. We've talked a lot about how a photon flies through space, how it doesn't feel the passage of time, and how it obeys the laws of the speed of light. But let's take a step back to the very beginning of this story, to the moment right before your room was plunged into darkness. Let's go back to the second when the lamp was still burning bright. We need to understand a fundamental thing. Where does light even come from? In everyday life, we intuitively think of light as some kind of substance that leaks out of objects, like juice squeezed from an orange or water leaking from a sponge. It feels as if deposits of light are hidden inside the metal filament, and the electrical current just frees them, pushing them out. But quantum physics tells us this is completely wrong. Until the moment the lamp was turned on, no photons existed inside it. They weren't hiding between the atoms. They are born literally out of nothing, in real time, as a result of a microscopic but incredibly powerful process happening inside the very structure of matter. To see this process, we have to mentally shrink ourselves billions of times and dive into the guts of your light bulb's tungsten filament. Tungsten is a metal, and like any material in our universe, it is made of atoms. For a long time, scientists pictured the atom as a solid, hard ball. Later, in the early 20th century, the planetary model emerged. The atom was thought to be like a tiny solar system where a heavy, positively charged nucleus sits in the center, and light electrons orbit it like planets around the sun. But this model was incomplete and full of contradictions. The main mystery was solved by the brilliant Danish physicist Niels Bohr. He applied those exact same quantum ideas we talked about earlier to the structure of the atom. According to Niels Bohr's model, electrons really do orbit the atomic nucleus, but they can't just do it wherever they please. They aren't free to choose their orbit. Imagine a tall staircase. You can stand on the first step, you can climb to the second, the third, or the 10th. But you physically cannot stand between the steps. You can't hover in midair at a height of 1.5 steps. An atom, according to Niels Bohr, works the exact same way. An electron can only exist on strictly defined energy levels, on what are called allowed orbitals. The space between these orbitals is a restricted zone for the electron. It cannot be there for even a single instant. The closer the step is to the nucleus of the atom, the less energy the electron needs to be there. The lowest level, the very first step of the staircase, is the electron's baseline, most comfortable state. Nature always strives to save energy, so if nobody touches the atom, all its electrons try to occupy the lowest, coziest orbits. But then you hit the switch, and the lamp lights up. What happens in that moment? A massive stream of directional electricity rushes through the wires to the tungsten filament. An electrical current is essentially a river of free electrons tearing through the metal's crystal lattice at huge speeds. And these speeding electrons begin to ruthlessly smash into the tungsten atoms. A brutal quantum car crash happens. An electron from the current, traveling at massive speed, slams into an electron peacefully sitting on the bottom step of a tungsten atom. In this collision, the flying electron's kinetic energy is transferred to the atom's electron. The atomic electron gets a massive energetic kick. Now it has way too much energy to stay on the bottom step. It has to move up. But, as we remember, it can't just smoothly crawl upward. It performs what's called a quantum leap. It instantly vanishes from the bottom step and in the exact same nanosecond materializes on a higher orbit. The tungsten atom enters what is called an excited state. It's pumped full of someone else's energy. But nature, as I mentioned, hates excess. It strives for harmony and minimum energy consumption. The atom's excited state is highly unstable. It's like taking a billiard ball and trying to balance it on the tip of a needle. The ball will stay there for a tiny fraction of a second and then inevitably slip and fall down. In the exact same way, the tungsten atom's electron can't stay on the top energy step for long. After a vanishingly small amount of time, millionths of a billionth of a second, it slips and falls back down to its rightful lower orbital. And this is where the climax of the whole process hits. The electron has fallen down. It no longer needs that excess energy it got from the collision. But the law of conservation of energy, one of the most fundamental and unbreakable laws of the universe, states energy cannot disappear into nowhere. The electron is required to eject this excess from the atom. It has to get rid of it. And the electron does this in the only way it can. It packs this excess energy into a neat, indivisible bundle of pure electromagnetic field and chucks it out into the surrounding space. This newborn bundle of energy is a photon. The moment the electron falls from the top step to the bottom is the moment light is born. Out of nothingness, out of the atom's pure energy debt, a material particle appears. This mind-blowing mechanism of interaction between matter and light was detailed in the second half of the 20th century under quantum electrodynamics, an ultra-complex physics theory for which the American physicist Richard Feynman won the Nobel Prize. According to this theory, all interactions in the electromagnetic field happen by exchanging or emitting photons. The color of the light we see depends solely on exactly what height the electron fell from. If it was on a low step and only jumped down a little bit, it dumps a small amount of energy. A photon with a long wavelength is born, red or infrared. But if the electron got kicked up very high, to the top floors of the atom, its fall back down is accompanied by a massive blast of energy. A blue, violet, or even invisible ultraviolet photon is born. Since trillions upon trillions of atoms in your light bulb's tungsten filament are colliding, getting excited, and cooling down all at the same time, they generate an unimaginable number of photons of every possible energy every single second. This chaotic, endless rain of red, yellow, green, and blue particles blends together for our macroscopic eye into a single, steady white glow from the lamp. But when you flip the switch the other way, breaking the circuit, the river of crashing electrons dries up. There are no more new collisions. The last excited tungsten atoms make their final quantum leaps downward, returning to a state of rest. They dump their final excess energy. The last photons are born. They break away from the metal, leave the glass bulb of the lamp, and rush into the space of your room, doomed to never experience time. They are born from an atom, and their fate is to die in an atom. The journey ends. The photon has crossed the distance from the desk to the wall, and now that 15th billionth of a second arrives. The timeless particle of pure light crashes into the surface of your wallpaper at full speed, with zero braking. What exactly happens in the micro world at this fatal instant? Can a photon bounce off, shatter into pieces, or does it vanish entirely? In the next chapter, we'll break down the physics of the inevitable collision and find out exactly what the death of light looks like. The journey of light has reached its finale. The photon, this massless, timeless bundle of pure electromagnetic energy, has crossed the space of your bedroom. In our macroscopic world, we only see the end result. The light hits the wall and illuminates it. But we've already agreed not to trust superficial glances. To understand the true essence of the death of a light beam, we have to mentally leave the familiar scale of meters and centimeters. We dive into the dizzying depths of the microworld, where the surface of ordinary paper wallpaper appears to us not as a smooth surface, but as a grand, highly complex architectural structure. Let's examine this barrier in detail. Your wall is covered in paint or wallpaper. From a chemistry standpoint, it's a complex conglomerate of molecules, long polymer chains of cellulose, complex organic dyes, microscopic crystals of titanium dioxide that give the material its white or light tint. Every single one of these molecules consists of tens and hundreds of atoms, tightly bound together by chemical bonds. The atoms are arranged in 3D structures, forming an incredibly dense crystalline or amorphous lattice. From the perspective of a flying photon, this wall is not a solid monolith. As the Austrian physicist Erwin Schrödinger, whose equations laid the foundation for modern quantum mechanics, showed. An atom is actually a tiny, heavy nucleus surrounded by a blurry cloud of probability. This electron cloud isn't a set of orbiting marbles as was previously thought, but rather a thick, vibrating fog of negative electrical charge. Atomic nuclei are located at colossal distances from each other by micro-world standards. Between them lies an overwhelming amount of absolutely empty space. And so, into this sparse, foggy, but electrically tense architecture, our photon bursts at a speed of about 300,000 kilometers per second. What happens the moment they meet? In classical physics, we are used to elastic collisions. If you throw a tennis ball at a brick wall with all your might, the ball compresses, deforms, transfers some of its kinetic energy to the wall, and then springing back to shape, bounces backward. The ball retains its shape, its mass, and its essence. It remains the exact same tennis ball. It just flies in the opposite direction at a slightly lower speed. But the quantum world knows no such mercy. The collision of a photon with a wall follows a completely different script. A photon has no mass that could be deformed or compressed. It cannot bounce off, retain its individuality, and lose some speed in the process, because its speed is an unchangeable constant of the universe. A photon either exists entirely, or it doesn't exist at all. It has no intermediate states. Therefore, when the flying particle of light approaches a pigment atom in your wallpaper, a process of complete and absolute absorption happens. But this process isn't random. It obeys the strictest rules of quantum censorship. The thing is, the electrons forming the cloud around the wallpaper atom are sitting on those exact same energy steps we talked about in the last chapter. Every electron has its own strictly assigned energy level, and it can only jump to a higher level if it receives exactly the amount of energy from the outside required for that jump. No more, no less. An electron is a perfect, ruthless quantum accountant. If the energy is short by even 0.001%, the electron will reject it. If there is more energy than needed to jump to a specific step, the electron also won't be able to accept it. To visualize this incredible phenomenon, let's look at an analogy from the world of acoustics. Imagine you walk into a quiet room where dozens of different metal tuning forks are set up on a table. Every tuning fork is tuned to its own unique sound frequency. One responds to a low C, another to a high A. You pick up a violin and drag the bow across a string, producing a clean, steady sound. The sound wave travels through the room and washes over all the tuning forks, but only one responds. Only the tuning fork whose internal natural frequency exactly matches the frequency of the violin's sound begins to vibrate. It absorbs the acoustic energy through resonance. All the other tuning forks remain absolutely dead and motionless, as if the sound never happened. The exact same quantum resonance happens the moment our photon dies. A photon is a bundle of oscillating electromagnetic field. It carries a specific frequency that determines its color. When it flies through the atoms of the wall, its electromagnetic field feels out the electron clouds of the paint molecules. If the energy of the flying photon doesn't match the gap between energy steps in the atoms, the photon just passes right through them, like through a void. This is exactly why window glass is transparent to visible light. There are no suitable energy steps in glass atoms for yellow, blue, or red photons. The light finds no resonance and flies straight through. But your wallpaper is opaque. The pigments in it were specially chosen by chemists to have a wide variety of energy transitions. And so, our photon finds its tuning fork. Its energy perfectly, down to the last decimal point, matches the energy required by one specific electron in the wallpaper molecule to make a quantum leap to a higher orbital. In the exact nanosecond that the condition for perfect resonance is met, an interaction occurs. The flying photon's electromagnetic field merges with the electron's electric field. A transfer of essence happens. The photon voluntarily gives up all of its energy, leaving nothing behind. What happens to the photon itself in this instant? It physically ceases to exist in the universe. It's not like water soaking into a sponge, because water stays water. It just hides inside the porous structure. A photon vanishes on a fundamental level. Its electromagnetic ripple completely smooths out, merging with the zero level of the quantum field. Its life, which lasted billionths of a second for us, but was a frozen eternity for it, is cut short. The light is dead. The flying energy of the particle has now become the internal tension of an atom in the wall. The electron has made its leap. It is now in a high excited orbit. The atom of the pigment molecule has become slightly heavier from an energetic standpoint. We turned off the lamp. The last photons darting around the room found their resonant electrons one by one in the wallpaper, the carpet, the wooden furniture, and vanished. The room was plunged into total, impenetrable darkness. Not a single flying quantum of visible light was left in the air. But the story doesn't end there. As we know, the universe doesn't forgive debts and doesn't write anything off into the void. The law of conservation of energy is relentless. The photon died, but its energy is alive. It got locked inside millions of excited atoms on the surface of your walls, and this massive hidden energy can't stay there forever. The excited state is unstable. The wall is required to react. What happens in the next instant after the light has completely vanished? To answer this question, we need to track the fate of this absorbed energy and learn how light is reborn into something completely different. We left our room in a state of deep darkness. Visible light has vanished. The trillions of photons that filled the space a second ago have been completely destroyed, absorbed by the matte surface of the wallpaper and wooden closets. An invisible energy drama is unfolding inside the walls right now. Electrons in the pigment atoms have jumped to high, unstable orbitals, soaking up the energy of the dead light particles. According to the laws of quantum mechanics, which we discussed in detail in Chapter 5, an electron cannot stay in a high orbit forever. It inevitably has to slip and fall back down to its baseline, comfortable resting state with minimal energy. Here a natural and logical question arises. If the electron falls back down, it is required to eject the excess energy. And we already know that this ejection of energy is the birth of a new photon. So why doesn't your wallpaper start glowing in the dark then? If the wall absorbed light, and then the electrons returned to their places, the wall should have simply re-emitted this light back into the room, like a giant, dim mirror. However, in practice, nothing of the sort happens. A dark room stays dark. Where does this colossal energy disappear to? The answer lies in the fundamental difference between the behavior of an isolated gas atom and an atom permanently soldered into the dense structure of a solid body. If we shined a light on a sparse cloud of gas, the atoms would indeed absorb the light and immediately re-emit it back out. This is exactly how neon signs or gas nebulas in deep space work. But your walls are solid matter. The atoms of cellulose and paint don't exist in isolation. They are tightly, inseparably bound to each other by strong chemical bonds. They form a single, massive, complex collective, a crystalline or polymer lattice. This tight packing changes the rules of the game. When an electron in a wallpaper atom falls from its excited high orbit back down, it has two paths. The first path is a radiative transition, where it simply ejects a new photon of light. But in a dense, solid body, this path is extremely unlikely. Instead, what kicks in is called a non-radiative transition. To understand how this works, let's imagine a giant trampoline where hundreds of people are standing tightly together, shoulder to shoulder, holding hands. This is our wall's polymer lattice. Now imagine that one of these people, the very atom that absorbed the photon, suddenly jerks and jumps high in the air. This is the moment of excitement. When he lands back on the trampoline net, he can't do it silently and in isolation. The impact of his feet on the taut fabric of the trampoline creates a massive wave that instantly travels through the linked hands to all his neighbors. The whole crowd on the trampoline starts slightly swaying and bouncing. The energy of one sharp jump was distributed among hundreds of participants, turning into a general collective wobble. This is exactly what happens in the structure of your wallpaper at the atomic level. The electron falls down, but it doesn't release energy as an ejected photon. Instead, the energy of its fall crashes into the chemical bonds holding the atom in place. The atom gets a massive mechanical kick. It starts vibrating, shaking. Since it is tightly bound to neighboring atoms, it jerks them too. This microscopic tremor rapidly spreads through the entire wall in all directions. In solid-state physics, this phenomenon has its own strict mathematical description. A quantum of vibrational motion in a crystal lattice is called a phonon. Note the difference in terms. A photon is a particle of light, while a phonon is a quantum of mechanical sound, a particle of matter vibration. The concept of phonons was introduced into science by the Soviet theoretical physicist Igor Tamm in 1930. Phonons describe exactly how thermal and acoustic energy flows inside solid objects. And so, the energy of the dead light turned into an army of scurrying phonons. Electrical excitement became the mechanical tremor of atoms. And what is the chaotic tremor of a massive number of atoms from the perspective of our everyday reality? Thermodynamics gives us the answer. It's heat. When atoms in a substance start vibrating and pushing each other harder and faster, the temperature of that substance rises. This is exactly how the first law of thermodynamics is formulated, the law of conservation of energy, which great 19th century minds like Julius Robert von Mayer and Hermann von Helmholtz fought to prove. Energy is neither created nor destroyed, it only changes from one form to another. The light that poured from your bulb didn't vanish into nothingness, it transformed. A pure, immaterial electromagnetic wave became the physical, tangible heat of your walls. In those seconds when you flipped the switch and the light went out, the surface temperature of your wallpaper, the carpet on the floor, and the wooden desk went up by a microscopic amount. Of course, on the scale of an entire room, this temperature bump is absolutely negligible. We are talking about millionths of a single degree. Human skin, even the most sensitive, could never detect such a tiny change. The thermometers in your bedroom won't budge. But for strict physics, the scale doesn't matter. The fact remains. Light energy turned into the internal energy of the walls. Light became heat. This process, called thermalization, is irreversible in everyday conditions. The vibrating wallpaper atoms will collide with nitrogen and oxygen molecules in the air of your room, transferring some of their kinetic energy to them. The air in the bedroom will also become unfathomably warmer. Then this heat will slowly start leaking through the concrete or brick outside onto the street and will eventually dissipate into the planet's atmosphere. The energy of the original light will spread wider and wider, becoming more and more diluted until it finally merges with Earth's background thermal noise. This is the greatest poetry of physics. The light you were reading a book by yesterday still exists. It is in your room right now. It just changed its mask. It's dissolved into the microscopic vibrations of the air you breathe and the trembling of the fibers in your blanket. But if we have proven with such mathematical precision that the light energy didn't go anywhere, that the room is still full of it, albeit in a different form, then a new, paradoxical question arises. Why then, when we look around after turning off the lamp, do we see impenetrable, terrifying darkness? If the room is full of photon energy, if atoms are constantly vibrating and emitting long-wave infrared radiation, why does our brain refuse to perceive it? To sort out this paradox, we have to make one last journey, but this time, not into the guts of the atom and not into the depths of space. We have to look inside ourselves. We have to understand how the most advanced and simultaneously most limited quantum detector on the planet works: the human eye. We'll talk in detail about why darkness only exists in our consciousness and what kind of illusion our brain spins in the next chapter. We've reached one of the most mind-blowing stages of our investigation. Solid-state physics and the laws of thermodynamics have convincingly proven to us that turning off a lamp doesn't empty a room. The space around you is still sparking and vibrating with energy. Walls are radiating invisible infrared waves of heat. The air is filled with the microscopic movement of atoms. The room is literally glowing in the long-wave band of the electromagnetic spectrum. And yet, when you lie in bed and open your eyes, you see none of this. Stretching out before you is an absolutely black, silent void. Darkness feels like a physical reality to us, like some kind of substance that has filled the room. But the truth is that darkness is not a property of the surrounding world. It is strictly a biological construct, a complex neurobiological illusion spun by your own brain. To grasp this, we have to look at the human eye, not just as a biological organ, but as a high-precision physical instrument tuned to detect quantum events. The back wall of your eye is lined with a unique tissue, the retina. It is, essentially, a piece of the brain itself, pushed outward. The retina is made up of millions of light-sensitive cells divided into two main types: cones, which handle color vision and bright light, and rods, which specialize in nighttime, black and white vision. When the light goes out in a room, the cones quickly give up and shut down. They don't have enough energy to function. The rods take over. Their sensitivity is downright fantastical. In 1938, the American biochemist George Wald, who would later win a Nobel Prize for his discoveries, figured out the molecular mechanism of how these cells work. He found an amazing substance inside the rods, visual purple, or the rhodopsin molecule. Rhodopsin is a complex protein structure that acts like a set mousetrap. Hiding inside this protein shell is a small, bent molecule of retinol, a derivative of normal vitamin A. It's in a tense state. When a single photon of visible light, whether it's green, blue, or dim red, enters the eye and hits this molecule, a microscopic quantum explosion happens. The photon's energy forces the bent retinal molecule to instantly snap straight. This process is called photoisomerization. By snapping straight, the molecule changes the shape of the entire rhodopsin protein structure. the mousetrap snaps shut. This shape change triggers a massive chemical cascade. One molecule activates an enzyme, which in turn splits hundreds of other molecules, which split thousands more. As a result, ion channels in the cell membrane close, the electrical balance is thrown off, and a sharp electrical impulse shoots down the optic nerve to the brain. The command is given. The brain registers a flash of light. This system's ability to react to a minimum amount of energy is mind-boggling. Not too long ago, as part of modern neurobiological research, scientists from Rockefeller University ran a series of elegant experiments where they shot single photons into the eyes of volunteers in completely isolated dark rooms. The results were stunning. The human eye is capable of detecting a single quantum of light hitting the retina. We are literally able to see individual elementary particles. But there is one critical detail that explains the illusion of darkness. This whole incredible biochemical rhodopsin machine is tuned by nature to perceive only a specific, very narrow band of energies, from 400 to 700 nanometers. That exact narrow spectrum of visible light. A photon has to pack enough punch to straighten out the bent retinal molecule. When you turn off the lamp, visible light vanishes, turning into heat. The wall starts radiating infrared photons. But these infrared photons are too weak. They carry too little energy. When a long-wave heat quantum like that hits your eye and smacks into a rhodopsin molecule, it doesn't have enough strength to uncoil the chemical spring. The photon bounces off, or is simply absorbed by the eye tissues as microscopic heat without triggering an electrical cascade. The mousetrap doesn't go off. The optic nerve stays quiet. And this is where the magic of your brain kicks in. When the visual cortex at the back of your head stops getting a steady stream of electrical impulses from the retina, it doesn't shut down. The brain has no idea how to just wait in a passive mode. For the brain, the absence of a signal is also a massive signal. Neural networks analyze this silence and generate an image of pitch-black darkness for your consciousness. The darkness you see isn't the view of an empty room. It's a projection of your own ignorance. The brain is literally painting a black canvas in your mind's eye, telling you, "I am not receiving data in the range I know how to read." You are blind to reality. If our eyes had evolved to see infrared radiation, like some species of snakes do, you would never know what pitch blackness is. Upon turning off the light, you would just see the white glare of the lamp replaced by a dim reddish glow from the walls, your own body, and your warm mattress. The room would look like it was bathed in the soft, pulsing light of cooling matter. Realizing that darkness is just a biological filter changes how we feel about the gloom of night. We fear the dark because ancient instincts warn us about the unknown. But physics reassures us. There is no void around you. You are surrounded by a boiling, continuous ocean of electromagnetic fields and thermal vibrations. You just close the blinds on your tiny window of perception. But what if we run a different experiment? What if we turn off a light, not inside a closed room with walls, but step out into an open field on a clear, moonless night and point a powerful flashlight straight up at the zenith, into the endless starry sky, and then flip the switch and cut the circuit. In this case, the photons bursting out of the lamp won't run into wallpaper, wooden closets, or pigment molecules on their way. They will pierce Earth's thin atmosphere, leave our planet, and burst out into the expanse of space. What will happen to these particles, which aren't destined to die in the very first milliseconds of their lives? Can they fly forever? Or will space itself find a way to wipe them out of reality? To answer these questions, we have to leave Earth and track the journey of light on the scale of the entire universe. We'll talk about this epic escape into the void in the next chapter. Up to this point, we've only looked at the fate of light inside the enclosed, cramped space of your bedroom. We found out that under those conditions, a photon's life is incredibly short, and its death is inevitable, and leads to the microscopic heating of your wallpaper. But let's radically change the parameters of our thought experiment. Imagine you grab a powerful handheld flashlight, step out into an open field on a deep, clear, moonless night, point the beam straight up at the zenith into the endless starry sky, and then hit the button and cut the power. Where do those last photons go? The ones that managed to launch off the flashlight's reflector billionths of a second before the bulb finally died. They no longer have a barrier like a ceiling or a closet in front of them. The colossal, terrifying abyss of the universe is wide open to them. Their initial path goes through our planet's atmosphere. Air seems totally transparent to us, but to a flying light particle, it's a thick, boiling soup of nitrogen, oxygen, carbon dioxide, and water vapor molecules. As our final volley of photons punches through the troposphere, stratosphere, and mesosphere, many of them die. They smash into gas molecules, get absorbed by them, and turn into heat, exactly like what happened in your room. Some photons scatter, bouncing off molecules to the sides. It's thanks to this exact effect, known as Rayleigh scattering, that a flashlight beam is even visible in the night air from the side. But a huge chunk of these light fugitives still manages to dodge fatal collisions. They rip through the exosphere at an altitude of a few hundred kilometers and permanently leave Earth's borders. They break out into deep space. At first glance, it might seem that now, finding themselves in a vacuum, these photons have achieved immortality. If there are no walls ahead, no planets, no thick gas clouds, then a particle flying at 300,000 kilometers per second, for which time does not exist, should fly forever. It should keep its energy intact until the end of time. But space hides a totally different kind of danger. This danger isn't hiding in collisions with matter, but in the properties of the space itself through which our beam is traveling. To understand what happens to this light next, we need to recall one of the greatest discoveries in the history of astronomy. In 1929, the American astronomer Edwin Hubble, spending his nights at the eyepiece of the giant telescope at the Mount Wilson Observatory, made a stunning observation. He was studying the spectrum of light arriving from distant galaxies and noticed a fascinating pattern. The light from the vast majority of galaxies was shifted toward the red end of the spectrum. What's more, the farther away the galaxy was, the stronger this shift was. This phenomenon got the name cosmological redshift. But why does light turn red? Hubble realized it happens because the galaxies are moving away from us. And they aren't fleeing because they're flying through empty space, but because the very space of our universe is constantly expanding. The fabric of the cosmos is stretching in all directions at once, like the surface of an inflating balloon. And here, we come back to our fugitive photons from the dead flashlight. They left the solar system, flew past the Oort cloud, and broke out into the interstellar void. Years pass, millennia, millions of years by Earth standards. The photons fly further and further away from their home Earth. But while they are on their way, the very space they are flying through is relentlessly expanding. What happens to an electromagnetic wave if the space underneath it starts stretching? The wave stretches right along with it. Remember our analogy from Chapter 2. Light is a ripple on an invisible lake. The distance between the crests of this ripple dictates the color we see. If the space of the universe increases in size, the distance between the crests of a flying electromagnetic wave also increases. If your flashlight was pumping out bright, visible white light, which contains short blue and green waves, then as it travels through the expanding universe, these waves will get longer and longer. First, this light will turn yellow, then orange, then it will turn into a deep, dim red. After billions of years of non-stop flight, the expansion of the universe will stretch these waves so much that they will permanently leave the visible spectrum. Our light will turn into invisible infrared radiation. Tens of billions more years will pass, and the waves will stretch to millimeters, becoming microwave radiation. And then, in the unimaginably distant future, they will turn into infinitely long, faint radio waves. And here, a profound paradox arises, one that stumped theorists for a long time. We know Max Planck's formula, which states, "The energy of a photon depends directly on its wavelength. The longer the wave, the less energy the quantum carries. If a photon flying through space stretches out and turns from high-energy blue light into a weak, low-energy radio wave, where does its original energy go?" Just a few chapters ago, we discussed in detail the inviolability of the law of conservation of energy. We said that energy can't just disappear. When light hit a room's wall, 100% of its energy transferred into the heat of the atoms. But in empty space, the photon didn't hit anything. It didn't transfer its power to anything. It just flew through an empty vacuum and gradually got weaker. Where did its colossal energy evaporate to? The answer to this question is one of the most counterintuitive conclusions of Albert Einstein's general theory of relativity. The thing is, the law of conservation of energy, the way we're used to understanding it from physics class, only works flawlessly in static, unchanging systems. If your room or your lab doesn't change size over time, the energy inside it is absolutely conserved. But the universe as a whole is not a static system. It is dynamic. It is expanding. In 1915, the German mathematician Emmy Noether proved a fundamental theorem linking conservation laws to the symmetry of nature. The law of conservation of energy stems directly from time symmetry, from the fact that the laws of physics today are the same as they were yesterday and will be tomorrow. But in an expanding universe, space-time itself changes every second. Space is bigger today than it was yesterday. This global asymmetry leads to a shocking conclusion. On the scale of the entire universe, energy is not required to be conserved. The energy of our stretched-out photons didn't transfer into anything else. It didn't hide in dark matter, and it didn't heat up intergalactic gas. It truly, literally, and permanently vanished from reality, erased by the very fact that the fabric of the cosmos is expanding. So, the light we shot up into the night sky, won't it die a sudden and violent death like the light in a locked room? A different fate awaits it. It will fly through the darkness infinitely long, but as it does, it will become weaker and weaker, paler and paler, losing its energy drop by drop. It will turn into a relic whisper, into an invisible, almost energyless radio wave that will wander forever through a cooling universe. Light won't die. It will dissolve into the expanding void. But if photons can pull off such incredible multi-billion-year journeys, it leads us to a mind-blowing thought. It means the empty space around us right now must be pierced by light that set off on its journey, at the dawn of time. We've arrived at the story of the oldest light in the universe, light that flared up long before not just light bulbs existed, but stars themselves. If we accept as a proven fact that light can fly through empty space for billions of years, slowly losing its energy, we inevitably arrive at a logical conclusion. If we point our radio telescopes at empty patches of the night sky, where there are no stars and no galaxies, we shouldn't see absolute silent emptiness. We should detect ancient light flying toward us from the very earliest stages of our world's existence. This is exactly what theorists working on the Big Bang model predicted in the mid-20th century. Physicist George Gamow and his colleagues argued that if the universe started in an unimaginably hot and dense state, then the primordial light from that colossal event must still be out there somewhere. It should permeate every point in space. But what did the birth of the very first light look like? Let's mentally rewind time back an unbelievable 13.8 billion years. In those distant epochs, there were no galaxies, no stars, no planets, not even the atoms we're used to. The entire colossal mass of the universe was crushed into a vanishingly small volume. The temperature was so terrifyingly high that matter couldn't exist in the form of chemical elements. Space was filled with a dense, roaring, blindingly hot plasma, a soup of free protons and electrons. And inside this boiling soup, an unimaginable number of photons darted around. There was an infinite amount of light, but the universe was completely opaque at the same time. Why? Remember our talk about how light interacts with matter. Photons only fly freely when nothing gets in their way. But in the early universe, free electrons swarmed everywhere like a thick fog. The second a photon tried to fly even a millimeter, it instantly slammed into a free electron, bounced off, changed direction, and flew a different way, where it immediately crashed into another electron. This process is called Thomson scattering. Light was trapped. It was locked inside matter. If you miraculously found yourself there as an observer, you wouldn't see past your own nose. You would be surrounded by a solid, uniform white glare of plasma. But the universe was rapidly expanding, and as a gas expands, it cools. A long 380,000 years passed after the Big Bang. The temperature of the cosmic plasma ocean gradually dropped to about 3,000 degrees Kelvin. It was exactly at this temperature that one of the most important events in the history of the cosmos happened, the recombination epoch. The kinetic energy of the particles dropped so low that free electrons could no longer fight the pull of the protons. They started falling into orbits around nuclei en masse. The first neutral hydrogen and helium atoms were born. The fog instantly cleared. The electrons that used to randomly block light's path were now neatly locked into strict energy steps inside atoms. For those exact photons that had been darting around in plasma for hundreds of thousands of years, endless, empty highways of new space suddenly opened up. They stopped hitting obstacles and rushed forward in a straight line. The universe became transparent. The greatest flash of light occurred, unmatched by anything before or since. This primordial light set off on its eternal journey. At the moment of its release, it was blindingly bright, with a wavelength matching the visible orange and red spectrum. But as we found out in the previous chapter, space doesn't leave light unchanged. The universe kept relentlessly expanding, and as it grew, this ancient red light stretched right along with it. Billions of years turned it from visible light into infrared heat, and then stretched it even more. Today, after almost 14 billion years of travel, this light has completely lost its original fury. It cooled down. Its waves stretched out to a few millimeters in length, turning into weak, barely detectable microwave radio radiation. The most amazing part is that humanity discovered this echo of creation completely by accident. In 1964, two American radio astronomers, Arno Penzias and Robert Wilson, were working with a giant horn antenna at Bell Labs in New Jersey. Their goal wasn't to crack the secrets of the cosmos's birth at all. They were just calibrating an ultra-sensitive receiver for satellite communications. But during setup, they ran into a frustrating problem. No matter how they pointed their antenna, no matter what part of the sky they looked at, their instruments stubbornly picked up a constant, steady, low-frequency background noise. The noise didn't change day or night, summer or winter. It came from everywhere at once, with the exact same intensity. At first, the scientists thought the problem was with the gear itself. They carefully checked all the wiring and resoldered contacts. They even climbed inside the huge antenna horn and scraped out pigeon nests, figuring the birds' droppings might be causing radio interference. But nothing worked. The mysterious noise stuck around. Soon, they realized a monumental truth. They hadn't caught interference. They had caught the very first light of the universe, stretched by time into the radio band. This discovery, which won the Nobel Prize, permanently proved the Big Bang Theory was right. It's the relic radiation, or the cosmic microwave background. The temperature of this ancient light today is just 2.7 degrees above absolute zero. It is the coldest light in nature. Realizing this fact changes our whole concept of darkness. If you are sitting in a pitch-black room right now, having turned off all electronics and pulled the curtains tight, you still aren't in a void. Your room, your body, the space between your fingers, all of it is being pierced right now, every second, by billions of photons of that exact relic radiation. This ancient light has been flying toward you for 14 billion years from regions of space that are now at the very edges of the observable universe. It passes through the brick walls of your house as easily as a sunbeam passes through clean glass, because most materials on Earth are completely transparent to such long radio waves. We literally bathe in the radio echo of the Big Bang every moment of our lives. Even old CRT TVS, the ones we used to tune with rabbit ear antennas, could pick up this ancient light. If you remember, when the TV wasn't tuned to a channel, a chaotic black and white static appeared on the screen, so-called snow. About 1% of that visual static on the TV screen was the direct result of relic Big Bang photons hitting the household antenna. You could sit in your living room and literally watch the remnants of the very first light in the cosmos. It turns out light doesn't go out. It can change its frequency. It can transform into heat. It can stretch out and become radiostatic. But it remains a part of this universe. But here, a curious mind has to ask the most fundamental, deepest question possible. If we claim that light transforms, changes shape, or gets absorbed, then what is the foundation it is woven from? If a photon is a ripple, and wavelength is the distance between crests, what exactly is rippling? What is the lake in our metaphor? In 19th century classical physics, scientists believed in the existence of an ether, some invisible, perfectly elastic substance filling all space, through which light waves propagated. But Albert Einstein in 20th century experiments buried the idea of a material ether forever. And yet, a void can't tremble. An oscillation must have a substrate. To solve this final mystery and understand the true, ultimate nature of the vacuum, we'll have to dive into the most powerful, precise, and complex theory ever created by the human mind, quantum field theory. This is what will give us the final answer to the question, where does light go when everything ends? We have come a long way. We've seen how particles of light are born from falling electrons, how they smash against the walls of a room, transferring their energy to atoms, and how they fly endlessly through cooling space, turning into the whisper of the cosmic microwave background. But until now, we've used the words photon and wave as objects of sorts. We pictured them as flying marbles, then as invisible springs. The time has come to destroy that illusion too. We need to go down to the most basic bottom floor of our universe's architecture. In the mid-20th century, brilliant theoretical physicists like Paul Dirac, Julian Schwinger, and Shinichiro Tominaga merged the equations of special relativity with the principles of quantum mechanics. The result of their titanic labor was quantum field theory, QFT, a concept that permanently changed our understanding of what reality is made of. According to this theory, the fundamental building blocks of the universe aren't particles at all. There are no solid marbles. The true, primary foundation of the universe is quantum fields. What is a quantum field? Picture an endless, invisible ocean that fills absolutely all space. It's present in every point in your room, inside your body, inside the nucleus of an atom, and in the most distant intergalactic void. This ocean is continuous and omnipresent, and there are many fields like this in nature. There's an electron field, a field for the quarks that make up protons, and most importantly for our story, there is an electromagnetic field. In its completely calm state, when the field has zero energy, it doesn't show itself at all. Math calls this state the quantum vacuum. We perceive it as total emptiness. But the second you introduce a burst of energy to this field, for example, when an electron in your lamp's tungsten filament falls to a lower orbital and dumps its excess power, a local disturbance happens in the electromagnetic field. A ripple appears, an energy spike. And this spike, this tiny knot of energy gliding across the fabric of the field, is what we call a photon. The field is the ocean, and the particle is just a fleeting wave on its surface. A photon doesn't fly through space as an independent object. It is space itself, or rather, the electromagnetic field stretched across that space, passing the disturbance from one of its points to another. To make this highly complex concept easier to visualize, let's imagine a regular acoustic guitar. The neck of the guitar is the space of your room. The string pulled tight across the neck is the electromagnetic field permeating the universe. The string is always there, regardless of whether someone is playing it or not. It is omnipresent. When you turn on the light, it's the equivalent of plucking that string hard. A powerful, vibrating wave of sound starts running down it. This traveling wave of tension is the photon. It glides along the string at the speed of light. And then this photon reaches a barrier, the wall. In our analogy, it's not the string itself that hits the wall, but the vibration. Imagine that at the other end of the neck sits a soft cushion or your palm, pressing tightly against the ringing string. What happens in that moment? The energy of the string's vibration transfers to the atoms in your palm, making them heat up. The sound cuts off. The vibration completely dies out and vanishes from reality. But did the string itself disappear? Of course not. It stayed right where it was. It is still stretched across the neck. It's just in a state of absolute invisible rest now. This is the exact fundamental event that happens when the light goes out in your bedroom. Darkness isn't a place where particles went missing from. Darkness is the state where the electromagnetic field in your room has stopped vibrating in the visible frequency range. The ocean calmed down. The string stopped ringing. But quantum field theory hands us one final surprise. It states that a quantum field can never, under any circumstances, be absolutely still. Even if you create a perfect vacuum, cool it down to absolute zero, and isolate it from all radiation in the universe, the electromagnetic field inside that vacuum will not completely stop. Werner Heisenberg's uncertainty principle kicks in. Nature abhors absolute precision. The field cannot have strictly zero energy. Instead, it boils constantly. In every microscopic point of an empty room, the electromagnetic field is endlessly jittering. Out of nowhere, tiny ephemeral energy spikes constantly pop up, which mathematicians call virtual photons. They appear in pairs, live for an unimaginably tiny fraction of a second, and immediately vanish, annihilating each other and returning their energy back to the vacuum. This isn't sci-fi or a theoretical fantasy. This boiling of the vacuum, known as zero-point field fluctuations, has been proven experimentally many times over. For example, thanks to the Casimir effect, scientists have measured how two uncharged metal plates in a perfect vacuum are drawn together, simply because the boiling virtual photons press on them harder from the outside than from the inside. And this means that absolute perfect darkness and silence do not exist in nature. Your turned-off nightlight is just a pause in a macroscopic symphony. While the room seems plunged into black, motionless gloom to you, on a quantum level, it is a roaring cauldron of zero-point energy. The light that poured from the lamp was just a loud chord strummed on the strings of the universe. That chord faded, dumping its energy into the heat of the walls. But the fabric itself, capable of spawning light, remains here forever. It waits. It permeates you right now. And all it needs is one single jump of a tiny electron, just one jolt of electrical current, for the ocean to stir again, and for a new wave of energy to rush through space, illuminating your world. Now we are ready to pull all these incredible facts together. We tracked light from its birth to its final transformation. And in the last, concluding chapter, we will summarize the philosophical and physical takeaways of our journey, forever changing how you think about what happens when you simply flip a switch. Our investigation is coming to a close. We started with a simple, everyday action, the click of a plastic switch in your bedroom. And it seemed like the result was obvious. The room went dark, and the light ceased to exist. But physics, step by step, shattered that naive illusion of emptiness. We found out that light needs time to die. In those imperceptible billionths of a second while our brain is just getting ready to process the darkness, millions of photons dart around the room, bouncing off walls and refracting through glass. We learned that a flying photon isn't a tiny projectile, but a timeless knot in the electromagnetic field, for which its birth on a tungsten filament and its death on matte wallpaper blend into a single, frozen instant of eternity. We went down into the micro world and saw how the atoms of your walls act as tuning forks, resonating and greedily absorbing light energy. The photon vanishes, but its colossal energy doesn't go anywhere. It crashes into the crystal lattice of matter, making the walls vibrate with microscopic tremors. Your nightlight didn't go out without a trace. It became invisible heat. It turned into an army of photons that is currently streaming through the wallpaper, heating the air and dissolving into the planet's breath. We looked up to the heavens and realized that light escaping our atmosphere faces a completely different fate. It won't die in a collision. It will stretch forever across the fabric of the expanding universe, losing its energy and becoming a quiet relic whisper, a radio echo of past eras piercing the cosmic void. But there is one final aspect of this process that ties everything together. It's the information paradox. When light turned into heat, and that heat dissipated around the room, it felt like the very essence of that beam was erased. But in fundamental physics, over which geniuses like Stephen Hawking and Leonard Susskind waged fierce debates, there's a strict postulate: quantum information is never lost. Everything that light was, its angle of impact, its wavelength, the moment it shot out of the lamp, all of it is mathematically stamped into the current state of your bedroom. If we had a hypothetical supercomputer capable of tracking the microscopic vibrations of every atom in the room, every fraction of a degree of heat, we could, like rewinding a movie reel, roll time backward. We could use the layout of that heat to reconstruct the shape of your lamp, the color of its glow, and even the exact second you flip the switch with 100% accuracy. The information about the light is eternal. It is dissolved into the structure of reality. And finally, we saw the true nature of the vacuum. Darkness isn't a place where an entity left. It is simply a state of rest for the electromagnetic field. The string piercing the universe stopped ringing in the visible spectrum, but it didn't go anywhere. It continues to boil constantly with zero-point quantum fluctuations, reminding us that absolute silence and emptiness do not exist in nature. Light never goes out without a trace. It transforms into the thermal tremor of matter, blends with the cosmic microwave background of space, or gets permanently stamped into the quantum history of your home. By flipping a switch before bed, we aren't killing light. We aren't destroying energy. We are just forcing it to change its mask, releasing it into a different form of existence invisible to our limited eyesight. It's funny to realize this while sitting in what seems like pitch-black darkness. You are surrounded by boiling quantum fields, vibrating atoms of heat, and relic light flying from the dawn of time. You are right in the center of an invisible, epic energy storm. I wonder what other mind-blowing secrets and invisible processes are hiding in those everyday things we're so used to calling absolute emptiness.